This session will be focused on the use of the Wireshark tool to help us to analyze and to troubleshoot the IPsec VPN. And I'm Jean-Paul. I've been working as a network and system engineer for more than something like 35 years. And since 2010, I'm run my own company as a consultant and a trainer. I've also published for the French publisher ENI several books. Among them, there is a book about the VPNs and another one about the IPv6. I must say, to be clear, that I'm in no way an expert in VPN, for example, but I hope to be a popularizer of the knowledge about these topics. You can reach me at the following address, jean-paul@jprconseil.com, and during the Sharkfest event, you can also reach me on the Discord tool. As you are probably aware now, I'm French, so please forgive me my accent, forgive me the several mistakes I'm likely to make during this session. I hope you will be able to understand me nevertheless. So let's start with the agenda. We will start this presentation by using Wireshark to analyze some IPsec VPNs with encrypted packets. We will mainly focus on IKE version 2 with or without network translation, network address translation, since it is the most commonly used version now, or it should be. But as version 1 is still used in several companies, we will have a couple of slides about this version. Then we will see if and how we can use Wireshark to decrypt IKE or ESP packets when it is possible, since it's not very often that we can decrypt. It needs some data that are difficult to find sometimes, but we'll see nevertheless if we can do this. So after decryption, we will see more information in the packets, and we will start again our analysis with packets decrypted. And finally, we will end this session by some troubleshooting to see how we can use Wireshark to help us to troubleshoot some cases where the VPNs doesn't run all smooth. To help us in this presentation, we will have some only a part are visible in clear in this case. And to help us, we will present the topology that we have based our example on. The first case will use two firewalls directly connected, site A and site B. And we will also have one firewall behind another device to present the translation case a bit after. So this is the topology we have used for all examples used in this presentation. The captures files and the profiles folders are available if you want to use them and to download them. You can go to the Discord channel Zoom number 2, where you will find a zip file containing some captures files and also some profile folders. Normally, you are able with the examples, the _charttest.zip to extract these files from this file and to be able to follow more easily my presentation, or to start again my examples after the session. The first case will be VPN with IPsec version 2. So we will go from site A to site B. There is no translation between the endpoints. We will use a specific algorithm and some public addresses that we will find in the capture file, and also some subnet that will be routed through the VPN. The file we will use for this example is the following one, example underscore IP2 underscore nonat.pcap. If we open this file, in this case, this is this file, we will see two parts in these capture files. The first part is related with the creation of the VPNs, and in version 1, perhaps we will call this one phases 1, and the second part will transport the user data. So let's see what is happening during the first exchanges. There are 4 packets to build an IPsec VPN in version 2. The first exchanges, packet 1 and packet 2, leads to the creation of the IPsec Security Association. That is always often named Parent Security Association. And the following packets, 3 and 4, are needed to build the child security association. And we can have several child security association per parent SA. For these exchanges, there are a role, initiator, and a responder. But this role could be, or can be, reversed for following exchanges. We can start parent SA from A to B, and then see creation of child SA, for example, from B to A. In this case, the initiator and responder role will be swapped. All messages work in pair. You have a request and you have a response. We'll see in the packet 1 and 2 what we can see. I suppress the packet bytes. This is not useful there. So the first packet, what is brought by this packet? The first packet is a packet of IPSA in its type, and you have a message ID. This message ID is important because you can see if you display this packet, this field, you can see the exchanges, and you can check that each request has a response, as you can see in this column. If there are resource suspicion, you must, or more precisely, the protocol must use the same message ID. After that, we have different types of data about the exchanges of some data for the key, for issuing the cryptography, starting the cryptographic process. You have some nuances. And also you can see that we have something related with NAT detection. In version 2, there is always a NAT detection probe that happens during the first exchanges to see if something between the point A and point B translates addresses. There is a digest sent and calculated and sent by the, let's say, the site A. So there is a digest of IP address source, the port source, and also the what we call the security parameter index, that is a good indicator of the conversation. Each conversation must have different SPI. So the combination of these three fields leads to this digest, and this is the same thing for the destination. And the same calculation is made by the receiver to see if something has changed during the travel. If it is the case, it means that there is some translation, and then we must switch to another way of sending or IPsec data, as we will see in further slides. We have also some algorithm. We can have several choice of algorithm proposed by the initiator, and then the responder send also some answers, some data, and if it is necessary, it chooses one of the algorithms proposed by the initiator. In this case, we can see that until the second packet, we see everything in clear. It's not the same with the following packets. With packets 3 and 4, we can see that we have a part which is encrypted. But we can nevertheless see the SPI, initiator, and now the responder, since in the first packet, there were the responder SPI was 0, since it was not known until then. Now we can see the initiator and the responder SPI, and we can see also the message ID. And we can see also some flags. These flags are useful to see if we are the initiator, if the message is an answer or a request or a response. And if we can use, which we could use, some higher version. In this case, as we are using the number 2 version, we don't have any higher version available. And then something that is encrypted, so not very useful for us for the moment. In the ESP part, that is supposed to transport the user data, not many information available. What can we see? In an ESP packet, very few things visible. The SPI, this is an SPI and index different from the previous one built or calculated in phases 1 or in the child creation. And you have also a sequence number. So we can add, we could add some columns to follow the SPI and also the sequence number. That will be useful for us to see if everything runs smoothly, a request and a response, and if packets are coming in the right order, this kind of thing. but that's all. If we want to get more information, we will need to decrypt these packets. So what do we need to decrypt these packets? We need first the SPI. It's very easy to get from the capture. We have already seen that we have this information in what we have seen until now. So we will get this. The most difficult part is to get the encryption keys, since they are not exchanges. They are not exchanged in the packets. So the only point where you can find these keys is on the endpoint, and it's not very common for the endpoint, for security reasons, to make this data available to anyone. For example, I have to use in this lab a SONG1 tool to get these keys from one end. If you remember, one end is a SONG1 endpoint, and the other one is a WatchGuard appliance. In the SONG1, I had to increase the log level to get these keys. I've put in the slide the command used for this. And if you have different tools, different appliances, you have to find if something is available for your device. The other point that is very important in this case is that these keys are only available and only recorded in the logs at the beginning of the conversation. So it is at the creation of the IPsec Security Association that we can get these keys. If you start the log or the increase of the log level after the creation of the IPsec, you won't get these keys. And on SONG1 tool, this is the results of the log, of the increasing of the log. And we can get four data, four fields interesting. Two fields for the encryption keys, one for the initiator, one for the responder, and two for the authentication keys. And the difficult point in this case also is that you have to copy this string, this hexadecimal strings, to put it in the Wireshark screen. Let's say, let's see how we can do this on Wireshark. When I have this famous keys, I will switch to another profile, and there, and to be able to show you how I have put these keys in Wireshark. In Wireshark, you can go to preferences, and more specifically to the ISA KMP protocol, where you can find two tables, one for the version 1, one for the version 2. In these tables, you will be able to enter the key previously found in the logs. You must be very careful not to mistype something, since as we will see, if something is wrong, you will get bad results either on deciphering the packets or in authenticating the packets. You have to put the SPIs that we have seen, the keys discovered in the logs, but also the algorithm that are used for the encryption and for the integrity. You can see that these tables are available in your profile under the path displayed there. If everything goes smoothly, so it was on this one I was using, you can see that there are some additional information in the column, for example, ID. And if I go to the packets 3 and 4 that weren't displaying many information useful previously, now I can see that there is a part named deciphered data. And in this part, I can see some very useful information. The first information very useful is the ID. It's very important in an IPsec VPN, but when building the initial VPN, the initial part of the VPN, it's very important to authenticate each endpoint. It is done with, for example, pressure key, but it's also done by the identity that we present to the other point. And it's very important that there is no mismatch between what I propose as my identity and what the remote point expects from me as an identity. This deciphered data permits to verify, check what identity I sent and what identity I expect for the initiator. And normally I can find the same thing for the respondent. This is the first important information that we can get from these unencrypted packets. The other one, in my opinion, is the traffic selector. Traffic selector is very important to run smoothly VPN, since it is what is used to decide if some packets will be routed via the VPN or via the default gateway, for example. And if there are some mismatch between what is sent by the point A and what is expected by point B, it can trigger a refusal by the receiver of some traffic. For example, if he sees some traffic coming from a subnet not present in its traffic selector. So it's very important to be able to check what traffic selector we are using, we are proposing to use in our VPN. And there are also some other information, but for me, it's the most important ones. If we check what we are seeing now, we have decrypted the ISA-KMP ports, but we are still stuck with encrypted packets for the ESP part. And this ESP part is the most important for us, since it transports the user data. So let's see what we can use, if we can use. This directly show you what was happening. So now we can switch to the slide with the Esp packet. In this case, we need also the index parameters, and we also need the algorithms. And now we have also to get we arrive to the difficult part. We have to get the keys, encryption, and authentication keys. On strong swan, you have also to increase the log level, and you have to use a specific command. And this specific command allows you to display the strings needed for the decryption for each site. So if we have, if we want to use these strings, we have to put it in Wireshark tool, and more specifically in preferences, and we have to reach the Esp part, and there we can find something that is empty now. If I switch to my profile, with a complete decryption, let's see what is included in preferences. Esp, and this is what we can expect. To see, you have to put the IPs, public IP addresses, the SPI, the keys, and the authentication or encryption algorithm. And if everything is okay, you can have access to the original data. You can see there that there were some pings, exchanges, ICMP exchanges. There are also a connection on a specific TCP port. And so you are able to see what we could have seen in an ordinary exchange without a VPN. There is still a layer of the Esp that we can see there. And now in this layer, if you remember what we have seen in the previous slides, we were only able to see the SPI and the sequence number. There we can also see authentication data. We can also see some padding data. It's not totally, it's not specifically important. The most important fields are the SPI and the sequence number. But so if I can, we can see the mechanism of requests and responses. Just to show you something specific, in this packet, I was able to decipher it since I'm able to see the traffic selectors, the identities, etc. But you see that Wireshark warns me of something wrong with this packet. Actually, if I unfold the fields, I see that Wireshark tells me that the integrity is not correct. It's only because I've put the right values for the encryption keys, but I've made a mistake on the integrity keys. It doesn't it does not forbid me. It to see the decrypted data, but the integrity checked fades. Okay, let's see what we have seen. Now, what happens if there are some translation along the path between the site A and now the site C? So now we will use different files. We can use, example, NAT C for the part captured on the C site and A for the other one. If we open the one of this example, we'll see that there is a strong difference between the previous case. In this case, if I display the port used, we are using the port 500 as usual for the beginning of the exchanges. But after that, we switch to another port, the 4500 port. And what is very specific of the NAT translation inside an IPsec VPN is that the ESP packets are also based on a UDP port, and this is the same one for 4500. So it means that in order to make possible the transport of the ESP packets between the two sites, in spite of the translation, they switch to another transport protocol, UDP, with a specific port. This is the main difference with the previous situation. And also, so we have some packets on this port. So to distinguish the IKE packet from the ESP packet, there is something very specific. There is a prefix included in each IKE packet header, are 4 bytes with zeros to be able to distinguish the IKE packet and the ESP packet. Since the ESP packet cannot have a 4-byte zero value because the first value in the first field in the ESP packet will be the SPI, and the SPI cannot be 0. So if we display the packet bytes, okay. Oops, pardon. We are able to see these 4 bytes there. If you display an ESP packet, we don't have the 4 bytes with 0. Just a couple of slides about IKE v1 to see the differences. Let's open the Vrt Modes as you probably know, in IKE v1, you have main mode and you have aggressive mode. In main mode, we have more exchanges to build a VPN. than in version 2. You have up to 6 messages, most commonly in most common cases, that we receive there. They are also on the port 500. And then you switch to quick mode to build the phase 2. And after that, you have the ESP packets like we can have in version 2. So in this case, you have 4 packets, pardon, that are unencrypted and 2 packets that are encrypted, as we can probably see there. The following mode that we can find, is the aggressive mode. The aggressive mode is quicker to build or to than the main one, but it is less secure. It involves less packets. In this case, you have only 3 messages, and they cannot, we cannot have any negotiation between the 2 endpoints. You cannot negotiate algorithm, time lives of the tunnel, since in version 1 timelines is negotiable. It's not the case in version 2, where each endpoint can manage the time life on its side. The decryption of the packets is rather similar to the previous one. The word the fields are differently named, but it is not very important. You have also to get an initiator cookie, which is the SPI, in fact, and also you have to get the key, so it is the same mechanism as we have already seen. The only difference is in the screen that you put your keys in. You have to use the IPv1 decryption table. And the result is rather similar to the previous case. Now we can now that we have seen how IPsec VPN works when everything runs smoothly, we can see some situations where something goes wrong. And now we can do some troubleshooting with the help of Wireshark. First case, between A and C, what we can see that the VPN is established if we refer to what we see on Stones 1 or what we can see on the device, the other device. We see apparently everything is okay, but we cannot have exchanges, no ping, no protocol, whatever you can imagine, apparently succeeds in between the 2 LAN subnet LAN. So, and also the other point is that you see when you observe the counters that only the outgoing counters change and increments. So if we look at what we have captured on site A and site C, if we open the let's see, for example, site A. We can see there that the first part apparently is okay. We have some exchanges with answers and response for the ISAK-MP part, but regarding the ESP part, it's different. Now we can see that apparently we can see only traffic going from our side to the other side, but no answer. So there are some agents. We send many packets without success, apparently, because there are no answers. And if we look at the other point, it's the same thing on the reverse side. Only outgoing packets, no incoming packets for the ESP part. So in this case, just by capturing the exchanges, we can see that something is missing between the point A and point inside C. And it's likely, the most likely explanation is that there is some device filtering traffic between these endpoints. It's a rather common issue since the first part of the exchanges are based on UDP ports, and these ports are very often authorized by the intermediary firewalls, for example. But the ESP part, if not translated, is very often forbidden. So there, Wireshark is a very useful tool. Let's see now another case. There, we have nothing established. We have no IPsec, no try, no IPsec SA, whatever version we are using. So it's time to open the troubleshoot file. There it is. And we can see in this case that there are very few exchanges. We can see that there is one packet from this site to the other one, and many packets from the other endpoints, and nothing else. So and if we display some other fields, like for example, the version, we can infer that something is wrong with the initial exchange. We can see there that there is a version 2 that is proposed, but on the other side, apparently, he is more prone to use the version 1. So if there is a discrepancy in the version between the versions used by each side, the VPN cannot be built. The version 2 and version 1 are totally incompatible. Both endpoints can use both versions, but on a specific VPN channel, you cannot negotiate. You can have only one version. So it is very important to have not to have a mismatch between the versions. And there we can see rather quickly what the problem is in this case. So one side must change its version. In case 3, it's rather similar. Nothing established, apparently. But if we open the relative capture file, we can see that the exchanges are very short in this case. And if we deploy the packets, since packet 1 and packet 2 are unencrypted, we can see what we are looking for. In this case, we can see that after the request coming from the site A, site B or site C, to be more precise, answer with a temporary failure message. So it means that on the very low, very primary parameters of the IPsec VPN, and more precisely on the ISAC IMP parameters, there's something wrong. There is a mismatch. It could be a mismatch in the algorithm. It could be a mismatch in the authentication proposal. So we don't have any more explanation. We have to look for explanation in the logs, and the side that will have the most precise data will be the responder. In IPsec VPN, the most important logs are always on the responder side. So you have to check in it what is wrong with our settings. And then we have to check and correct, if necessary, the settings on both sides or on one side. It depends on the reasons. I've still some time. Now we have progressed a bit in the establishment of VPN. We have an established IKSA, but we have no child or IPsec SA built. There we are annoyed because we cannot see a lot of information in these exchanges. Since, as we've seen previously, only the first packets are in clear. When it is related to authentication, to traffic selector and all these things, or IDs, you must, this information is present only in packet 3 and 4, and these packets are encrypted. So we cannot expect to see much information in these exchanges. And it is a case where we need an encrypted packet, on the contrary of the cases that we have seen already. So if we decrypt, as we have seen, and I insist a bit, but it's not very frequent that you have all the information necessary to decipher the exchanges. But in this case, we have what we need. And in this case, and I will open the troubleshoot B file. In this case, I will switch, but in this case, I will switch to traffic probably more visible there. We have a message that is rather clear. Traffic selector unacceptable. In this case, it means that there is some mismatch between the two endpoints on about the subnets that are supposed to be routed by or via the tuner. And in this case, in this slide, we can see, if we pay attention to the traffic selector columns that we can also display with Wireshark help, we can see that there is something strange between what in packet 5 we propose from the site 56 and what the other site proposes. There is a mismatch, apparently. One is using 10.0.10 subnet. The other one intends to use the 10.0.30 .net. And so it's not possible to build a shard based on this data, since there is no common subnet available between the two sites. In version 2, you can have some subnetting inside the traffic selector, but if there is nothing common, it's not possible to build the child. So it's a reason there where why we reject the build of this tuner. Lastly, I think I have a couple of minutes available again. Still a couple of minutes available. So let's see the last case. Symptoms are rather similar. There, it is very, very short. Since we are on a problem with ESP, if we don't have unencrypted packets, we won't see anything significant. So if we decipher the exchanges there, we can see in this case that there is a response, no proposal chosen. And in this case, that means that there is something wrong in the settings that we propose to use. It could be the Diffie-Hellman group, it could be perhaps the encryption algorithm. So we need to check the settings. Wireshark there won't be very, very useful to discover what is wrong. The only thing that Wireshark can help us to discover is the message, the error message sent by the responder there. No proposal chosen. I can find perhaps the reason in the logs of the responder, since, as said before, the responder side gets the higher level of logs. In no case, the initiator will have very, very detailed information about what is wrong about the settings of the build setting up of the VPN for security reasons. The responder, when sending no proposal chosen, doesn't tell the initiator what is wrong in his proposal to avoid to unveil any useful information for a potential hacker. Okay, So I think I've reached the end of my session. Thank you all for your attention. I think that there is a session a survey, a session feedback. I think you have the link in the Zoom channel, I think. You can also reach me via my email address. You can reach me by you can reach me, pardon, with my Discord account, or also at least during the Wireshark event. Now,
sorry to interrupt. We can also open for Q&A if you want to do that, if anyone has any questions. Yeah. And thanks for a great presentation, Jean-Paul.
Thank you. Yes, you are right, Ali. Thanks for bringing this to my attention. Now it's time to questions if you have some, in the limit of my skills. Johan, yeah, to decrypt the streams, either the IC1 or the ESP1s, we need to get the keys, and these keys are not available in the captures since they are not exchanged. They are calculated. The 2 points calculates their keys with something they exchange between them, but in no case you can deduce or you can find the keys from what we see in the captures file. So in the captures file you can see the SPI, you can see the algorithms, you can see the IP addresses if needed, but the keys have to be recovered from at least one of the side, and the easiest one in this case, in the case of my lab, is on the StrongSwan tool, since the other device doesn't allow me to display these keys. It's understandable since it's a point of, it could be a point of security issues. Yeah, that's all I can say. So that is the difficult part of in this point. So it's the reason why it's not very common to be able to decipher the session. Yeah, Sake, I think I will have to check, but I think that I have no example on this computer, but I think that the encryption algorithm and everything linked with the setting up of the VPN are included in the VPN logs. I don't remember exactly what kind of log level you need for this, but I think you will be able to get this algorithm. And so perhaps, yeah, you can do a script, or you can make a script to create the entries. Yes, I've never thought of that, but perhaps it's possible. Yeah, it's good idea, good tip. Anders, have I any experience with extracting these keys from the IPv2 version of available on Windows 10? To be honest, no. But it's a very good question. I will look for this. Because you know, in my experience, the most common use of VPN for me and for the companies I work with is either site-to-site VPN, and the remote. I haven't told anything about the remote remote access to a site via an IPsec VPN. And so I've not looked for this information until now, but now I will be curious about this. Yes, I will look for this. I don't know, to be honest, Anders.